Okay guys, I'm going to try my best to keep this focused on the board. Also, I'm really sorry about the reflection. Okay, so today we're going to look at empirical formula. Reminder, we did do this last year, but just a reminder, it is the formula giving the proportions of elements in a compound, but it does not actually give the number or the arrangement of the atoms. Okay, so we don't know how many atoms are present, but we can figure out what the ratio is. That's what the empirical formula tells us. Okay, and just sort of in layman's terms, it is the simple version of the chemical compound. Okay, so that in red is our formal definition, and then this in green, it is the simple version of the chemical formula. Okay, so just for an example, if we have a chemical formula of C4H8O2, if this is our chemical formula, then our empirical formula for this would be the most simple version of it. I don't know if you guys can see that green. Okay, I won't use green anymore. Sorry about that. Okay, so the most simple version of C4H8O2 would be C2H4O1, but remember we don't write the ones as our subscripts. Okay, so empirical formula, basically just the most simplified version of the chemical formula of a substance. Formal definition, it is the formula giving the proportions of elements in a compound, but not the actual number or arrangement of atoms. Okay, so with empirical formula, generally you're going to be asked this just before the stoichiometry questions. Okay, and there is a pretty simple method that I want you to use. So I'm just going to jump straight into an example. I'm going to do two. I'm going to do one more sort of straightforward one and one that's a little bit trickier. Okay, so for example one, hoping we can see that. I think so if you kind of squint. Okay, so for example one, we're going to look at a scenario where we've got a sample of acetic acid. Okay, so we've got a sample of acetic acid, and it contains, and they will usually either give you the masses of each element or they will give you the percentage composition. Okay, so either way, it's the first thing we need to do is actually get the mass of each. So if they give you the mass, you're sorted. If they give you the percentage, then I don't know if you can remember back to last year, we have to pick a basis. Okay, so for this one, we're going to say containing 39.9% carbon. And 6.7% hydrogen, and the remainder, so that's 53.4% oxygen. Okay, and we are going to determine the empirical formula. Okay, so on your note that is on OneDrive, and I also sent it to the group, you'll see the little template that I want you to use every time you are asked to determine the empirical formula. So that's the key word here. If you're asked to determine the empirical formula, you're going to set up a table. Now bear with me, can't draw straight lines, I'm going to try my best. But what you basically need is you need one column for every element you have, plus a column on the left. So we've got 3 elements here, so I'm going to need 4 columns. Okay, so I'm just going to try my best here. Okay, there are my 4 columns. Then we need 1 row for our headings. And then we need a row. 1 row for the mass in grams of each thing. 1 row for the number of moles of each species or each element. And then depending on the question, you might need 1 row for the ratio, or you might need a second row if your first ratio is not a whole number. Okay, so for now I'm going to go with 1 row for the ratio. Ideally we can stop there. If in this row we do not have a whole number, then we need to put in another row. Okay, but what our columns are, so we skip one. Our first column is going to be carbon, then hydrogen, then oxygen. And we need to first determine the mass in grams of each element. Then we need to determine the number of moles. And please do write the formula of how you are going to determine the number of moles, because that is worth a mark. Remember, formula always worth a mark. And then in our last row, we're going to find the ratio. And just a little reminder, I'm hoping you do remember this, but for your ratio, you're going to take the number of moles of each and divide it by the smallest number of moles. Okay, so let's go for it. Now our first row, we need mass of each one of these. Now we aren't given mass, we're given percentages. So we need to go from percent to mass. They don't tell us what the entire sample weighs, what the mass of the whole sample is, so we have to just make some kind of an assumption, okay? So we're going to assume, or we're going to take a basis of, and now it's up to you, but it's probably best to choose 100 grams because it's very easy to go from percentage to a mass out of 100, okay? Because 39.9% of 100 is 39.9. So we pick a basis of 100 because it makes life easy, which means carbon's mass is going to be 39.9 grams, hydrogen's mass will be 6.7 grams, and oxygen's mass 53.4 grams. Okay, so first off, we need the mass of each element in the sample. Next up, we need to determine the number of moles of each element in the sample, just something that I occasionally see occurring, this M, that molar mass. That is not the molar mass for the entire sample, that is the molar mass for each individual element. So when we're doing carbon, we use 12, the molar mass of carbon, which is 12. Okay, hydrogen we use 1, oxygen we're going to use 16. So this M is the molar mass per element. Okay, so you use that element's periodic entry. Okay, so for carbon, we're taking the mass of carbon and dividing it by its molar mass to determine its number of moles. So we're taking 39,9 dividing by the molar mass of carbon, which is 12, and we get 3,325. Okay, remember you always round off only at the very end. So for now, we keep as much as possible. Then hydrogen, we've got 6.7 grams of hydrogen. And depending on your periodic table, you might have 1 as the molar mass, you might have 1,01. We normally go with 1. And we divide and we get 6,7 moles of hydrogen. And now we're going to do the same thing for oxygen. We've got 53,4 grams of oxygen divided by its molar mass of 16. And we get 3,375. Okay. Then last off, to find the ratio of each, this last column, for this we take each mole value that we've just worked out and we divide all of them by the smallest of the 3 mole values. So my smallest mole value here is this 3,325. So I'm going to divide this 6,7 and 3.375 all by my smallest 3,375. Okay, so when I divide 3,325 by itself, I get 1. When I divide 6,7 by 3,325, I get round about 2. It's close enough to 2 to round off. And when I divide 3.375 by 3.325, I also get close enough to 1 to call it 1. Okay, so these ratios, 1 to 1, those tell us the ratios of our elements. Okay, so for carbon, we've got a little subscript bonding ratio of 1. For hydrogen, we're going to have 2, and for oxygen, we're going to have a 1. So our empirical formula for this sample of acetic acid is C, remember we don't put the 1, H2, and then O, again we don't put the 1. Okay, now the question comes in of when is it okay to round these values off to a whole number and when is it not, because they must be a whole number. Okay, you cannot have decimals here in your bonding ratios. It has to be a whole number, so we now need to figure out when is it okay to round off and when is it not okay to round off. So the general rule is if you have something, 1, you can round off downwards. If you have something, 9, you can round off upwards. but anything in between. Okay, you need to actually multiply all of your ratios by something, some factor that will make them whole. Okay, so general rule, if you've got something comma 1 or something comma 9, you can round off. But as soon as you have anything between comma 1 and comma 9, you have to actually multiply all of them by a certain factor to get to a whole number. Okay, and that's the next example I'm going to show you. I do think I'm going to split this video into 2 though, because I don't know how long it can be. It's already 10 minutes, jeepers. Okay, sorry.